Hey, what's up guys? Jeremy here from RoboDK. In this tutorial, I'm going to show you how you can position this part in the virtual station so that it matches the actual position of the part in the real world. So in other words, I need to show RoboDK exactly where this part is with respect to the robot base we have here. Now that we defined our TCP here, so the tool center point XYZ with respect to the robot flange, we're able to use that position in that robot as kind of a probing tool to teach RoboDK this specific position. As for now, I don't need to have my TCP definition tool. I can remove it, and that's a great idea if you don't want to, let's say, crash it with the robot. And I would be able to move the robot around and take some positions. But before doing so, I'm going to go back to RoboDK. As you can see in RoboDK, I have my part, which was placed pretty much arbitrarily in my station. You can also see that I have a reference frame called frame part right at this corner here. Again, the position of this frame was completely random. We don't really like random. In robotics, we need to be precise. So we'll see how we can teach RoboDK where this point is actually. As you can see in my station, the reference frame part is the parent of the part itself and all the paths that I want to follow in my station. So if I move the reference frame part around, the part and the paths curve points will follow. So in other words, if I define the position of that specific reference frame, everything within that reference frame should be positioned properly with respect to the robot base. One small detail that you need to take into account is that the frame part need to be a child of the reference frame base of the robot. Otherwise, the process that I'm going to show you right now won't work properly. Before doing the actual reference frame definition, I'm going to see if the position I have now in my virtual station is anywhere close to the real position I have here. So to do so, pretty simple. I'm going to bring the robot to one of the edge of my part. So as I have this, don't need to be super precise, just want to be near the edge. As RoboDK and the route controller knows the position of the TCP XYZ with respect to the flange, they should be able to retrieve that position with respect to the robot base. So let's do that using the connect on robot command and click on flange XYZ. As you can see here, we are quite far from the actual position. Not that far, but at least a few centimeter, which is not suitable in this situation. So the next step will be to use a tool called define reference frame. So utilities, define reference frame. Here, first thing to do is to select the right reference frame at the top. So here we'll select frame part. Then it's pretty much the same concept as when we were doing the TCP calibration. So I will bring the robot to a certain position, we'll record the position, bring the robot to another position, record the position, and we'll do that for 3 points. The important thing is to understand well the little figure you have in front of you. So there's different method to define a reference frame. The first one is the 3-point method we have here. I really recommend this one. So pretty much what you'll do is take a first position, if your origin is here, take a first position along the edge here, take another position along the edge here. So this will be X1 and X2. The algorithm behind RoboDK will be able to define the X axis along that edge. And then you probe another position here along the Y-axis on this edge here. So RoboDK will be able to define where the origin is, and by convention, we'll know that the Z-axis, will be pointing upward. Another method available is the 3-point method using the origin. A first point on the origin, a second point along the X-axis, and a third point on the XY plane. In this case, this is not a suitable method or algorithm because the corners of my plate are rounded. There is like a radius of 7 millimeters. So it's pretty much impossible to know the exact position of the origin. The last method you can use is the 6-point method, where you need to get 3 points along the XY plane, so anywhere on the XY plane, 2 points along the XZ plane, and 1 point along the YZ plane here. This method, again, is not very suited for my situation here, as I can't really reach with the robot here, and I don't have that much space to take those points, but it's another option. So you'll see, depending on your specific part or specific jig, which method you would prefer using. Let's actually run the method. So first of all, for the exact same reasons as we've used the pause instead of the joints for the TCP calibration, we'll switch the drop-down menu to pause, and then I will bring my robot as close as I can from the origin and directly on the edge of the part here. And obviously I'm just driving it in free drive right now, so I can't really have a super good, let's say, accuracy because I'm doing that manually. So I'm going to ask my colleague to just bring the robot up a bit in Z. Again, Z plus. Again, 3 or 4 times. Again. Okay, go for X minus. Z plus once. So one way to make sure that you're quite precise in such a situation is simply to grab a piece of paper and see if you can slide it underneath the part in the corner and see how close you are. So in this case, I'm close, but not close enough. So I'll ask for X minus 2 times. Okay, that seems better. So now I can barely fit a sheet, so this is perfect. Okay, so now I'm going to record that position using the command and then flange XYZ, sorry. Okay, so one thing you need to keep in mind is that to have the best TCP definition, TCP calibration and frame definition, you need to keep the robot in the same, as much as possible, in the same configuration. So a good way to do that is to simply move using the free drive, but just in XYZ. Because if you rotate joint, especially around the wrist, if you rotate the wrist a bit too much, the configuration and kinematic will be a bit off, and the actual position you'll get will be a bit off, so you won't be as precise. So this will highly depend on how precise you need to be for this particular path. So if you're doing just, let's say, glue dispensing, you don't need to be like 0.5 millimeter, let's say you don't need a precision at 0.5 millimeter close, maybe 1 millimeter is enough, so you don't need to worry too much about that. But if you want to be precise, I recommend you to use the same calibration. So if I am in free drive XYZ, I'll be able to keep the same tool orientation and just go as far as I can along the x-axis. So I recommend being as far as possible from one point to the other. The farther you'll be, the less error you should see. So Z plus 3 times. Okay, just like this. Take my sheet of paper real quick. So this is good. There's just barely enough space to run between the TCP and the part. So I'm going to record that second position. So again, according to the figure we have in front of us, we now got 0.1, which is x1. We got 0.2, which is x2. So RoboDK will be able to calculate the x-axis, this way. And now I need to give it the Y position. So again, I'm going to go along this edge here. Try to be as close as possible with the free drive. And then I'll ask for Y plus 4 or 5 times. Okay, Y plus once again. Perfect. So this seems to be quite precise. So now if I record this position, now you can see that we have an update button at the bottom of our screen. We can click on it. It will ask us if we want to actually update the position of the reference frame in the virtual station. And if we do so, you'll see that the reference frame and the part will actually move in our station. Perfect. So now that it's done, you can already see that now if we go closer to our TCP, the TCP is now right on the edge where it's supposed to be here. Let's do another test. So if I bring the robot, let's say this time right here, I'm not exactly on the edge, but I'm really close enough to know if that makes sense. So you can get position and can come closer and see that our TCP is pretty much on the edge. You shouldn't look at the actual 3D model of the tool at this point, because as you know, we redefined the position of this without any regard to the 3D model we had in RoboDK. So the Cartesian coordinates that you have in front of you are the actual position here. So it's quite good. Now let's say, so this one is easy because it's within the line that we probed. Let's go for another one a bit harder. So let's go right on this corner here. So, okay, let's go for this one here. We'll see if it does match. If you can go closer, you can see that our TCP position is pretty much on the corner. So this is cool. So this is a good way to validate if your reference frame definition is working. You just have to move around a bit. You take a few known points in your station. Obviously, the CAD model that you have in your RoboDK station needs to match the actual CAD you have, or the actual part you have here. You can take another point. And if we go closer, we can see that we are, again, right on the money here. So right on at the end, perfect. I'll go get another point here. Let's say this one, oops. Not always easy in free drive. Okay, so let's guess this one. I'm just a bit over in Z, so if we have a small discrepancy in Z, that's normal. So we are close. As you can see, the farther we go from the origin, the more likely we are to have a small discrepancy. So here we start to have a small error. We're maybe 0.5 millimeter away from this edge here. Yeah, but I'm myself at least 0.5 millimeter away. So I'm just gonna try to get a better, let's say, XYZ position on this one here. Okay, get the position again, please. Okay, as you can see now, we're quite close to the actual corner. So now we're really zoomed in, so it looks worse than it is. And if I go further away, the further I'll be from this corner, the more error I can expect. So if I just, let's say, move here, okay, get this position here. But we are still very, very, very close to the actual corner that we are looking for. So if you want to be more precise, let's say for this half of the part, one method that you could use would be to create another reference frame here or here. and create the toolpath around this section here with respect to those origins. So the closer you'll be from the origin or the reference frame, the more precise you'll actually be. That was how you can calibrate or define the position of a part with respect to the robot base within RoboDK, so that the virtual station does match with your real station. The goal here is to be able to generate complex paths, so the one that we generated earlier, and be able to actually run them, and that the position that RoboDK will generate, because it knows that this point here is at XYZ position, and then it will create, let's say, this curve here, so that when the robot runs, it does follow this curve here accurately, or as accurately as the robot is actually able to be. Okay, I hope it helps. Have a great day, guys.